Okay, so this is number 9 from the optimization handout. The picture is like this. You have a rectangular piece of cardboard. What was it, 16 by 30?
Yeah.
So 16 by 30 inches. And the idea is you're gonna cut out little squares out of the corners and then bend up, like, so this is just gonna be like thrown away. And then you're gonna bend up the edges to form like an open tray. So it will kind of look like this when you're done. And everybody kind of envision what's happening here. So you're basically folding along like these lines right here, green lines. Okay? So if we follow the process for an optimization problem, the first step is to draw a picture and assign variables. Let's have x be like the dimensions of the little squares that we're removing, right? So that corresponds over here to be the height of the box, right? The height of the tray. So then the second step is to write any equation for the quantity that you're trying to maximize or minimize. What are we trying to maximize or minimize in this problem?
Volume.
The volume of the box. We're trying to maximize the volume of the box, right? So if the other dimensions of this are like length and width, for example, the volume of the box is L times W times X, right? Length times width times height. The next step is to use the constraints of the problem to get rid of all but one variable. Well, how can you write L in terms of X? 30 minus 2x. And W? 16 minus 2x. So this ends up being 30 minus 2x times 16 minus 2x times x. That's the function that we're trying to maximize, right? So let's simplify it first. It might seem like a lot of work to do the FOIL here, but it'll save you time in the end because you don't have to do the product rule within the product rule, which is what you'd have to do otherwise. So I'm going to FOIL this out. I'm going to FOIL the two binomials and distribute x at the same time. So 30 times 16 is 480x, because there's an x there. 30 times negative 2x is negative 60. So this is negative 60x squared. 2 times 16 is negative 32x squared. And then 2x times 2x is plus 4x cubed. Right? So this ends up being 480x minus 92x squared plus 4x cubed. And then don't forget to consider endpoints. X has to be somewhere between 0 and 8, right? It can't be more than 8, because then you wouldn't be able to get like 2 squares out of one side. So it has to be between 0 and 8. Right? So to maximize a function, you take its derivative, you set it equal to 0, blah, 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 right? So this is going to be v prime equals 480 minus 184x plus 12x squared. Right? Set this equal to 0. It seems like we should be able to take out, no, I was going to say maybe a 12, but this is not divisible by 12, is it? So that won't work. What?
This is where
But at least a 4, no?
So yeah, so you can at least take out a 4. Or you can use technology. You can solve this using your graphing calculator. That would work. Let's just see if it's factorable. I don't know if it is or not. So this, if you take out a 4, you get x squared minus, what is it?
That would be 3.
Oh, 3x, yeah, thanks. If you take a 4 out of here, what do you get? Let's see.
It's like 46. 46, yeah.
46 x plus, take a 4 out of there, 120. I don't know if this factors or not. I'm going to use a calculator. So on my calculator, I'm just gonna graph the function. So I have 480 minus 184x plus 12x squared. By the way, on Tuesday's test, you can use your calculator. And you're always allowed to use your calculator to solve an equation. So that's what I'm doing. I'm using this calculator to solve an equation. So I'm going to graph it within the window that it's valid. So from 0 to 8, zoom fit. This is a little weird. Why does it look like that? There's no like clear max or min. And why is this negative? That makes no sense, right? So there's a problem somewhere. Let me just make sure I didn't make any mistakes.
I think this problem is just stuff.
What?
This problem is just stuff.
I don't understand what you're saying. It's what?
Stuff.
What does that mean?
Like
Scuff?
stuff. Yeah.
Oh. I know. Shut up, Josh. You're grounded. All right, let's see. Don't see a mistake. So maybe I made a calculator error. Let's see. 480 minus 184 plus 12. It seems okay.
Wait, when do you graph the
Oh, what the
original thing?
Yeah, what am I saying? No, okay, that's the mistake I'm making in my brain. In my brain, I'm going, whoa, why isn't there a maximum? This isn't f of x,
Yeah.
this isn't the volume, this is v prime. So we just want to know when it's 0. It's definitely 0 right there. All right, so calculator, 0, left bound, right bound, and yes. So it's 3.333. This must be factorable, but who cares? So if this was a calculator part of the test, you'd write the setup, and then you just say x is equal to 3.333. Done. That's all you have to write. You don't have to do any other work there. And then you do have to do your first derivative chart, though, to ensure that 3.333 yields a maximum and not a minimum. So when you do your first derivative chart, it's going to be v prime, 0 and 8, and 3.333. You can see from your chart, or from your graph, it's positive and then it's negative, right? It's above the x-axis, then it's below the x-axis. So it's positive, then negative. You can see clearly that that's a maximum point. So this question is asking you, let's read the question. What size should the squares be? They should be 3.333 by 3.333 inches. That's the answer. Okay? Does that make sense? So the hard part about this was the algebra, not the calculus, right? Okay, good. That's a good thing, I think. I'd rather have you have a hard time with algebra.
That's not your fault.
No, because algebra problems are easy to fix, I think. More so than like calculus understanding problems. All right, what else? Any other questions on the handout itself? Or I have a couple interesting problems if you want to do that instead. Any more of these you want to do? You guys got this one already?
Yeah.
You did?
I want to do that on my own.
Okay. This one was pretty hard.
Yeah,
I mean, if you want to
and
do it,
if like you do, because I haven't like started it, to be honest, like if I do it tonight and then like tomorrow in our class, can we just ask questions?
Of course.
on this one?
Yeah, of course. Yeah, okay, so I'll give you a chance to try it on your own if you haven't tried it yet. Don't forget, I will be having just a Google Meet. It's optional. You can come if you want. And it's during third period, which is 8:43 to 9:04 tomorrow. So if you want to just go to the Google Classroom page and click on the regular Meet. I'll just be here to answer questions. Okay? So it'll be on any of this stuff or any of the personal progress check questions or anything like that.
Are you gonna, if there's if there's people asking questions, are you gonna record it?
Yeah, I will. Another thing that some people were requesting in the last test that I should have been doing all along, but I didn't, is I actually created another assignment in AP Classroom that just has a few more questions that you can sort of use as like a pretest. You can like pretest yourself after we go over the personal progress checks or before or whenever you want to. It's just another set of questions that are going to be similar to questions that are going to be on the test. So it's totally optional. You don't have to do that. And I think it's called like Unit 5 review or something like that. So do it if you want to, just to test yourself. And you can ask me questions about that at any time also. Okay, so let's just do a couple other problems for optimization. So what about this one? This one I thought was pretty interesting when I saw it. It was kind of hard to figure out what to do. So suppose you have a curve, a sine curve, okay? So this is the graph of sine x. This is f of x equals sine x. And suppose you have a rectangle that's inscribed in this curve. So something like this, a rectangle that looks like this. So it fits inside one of the little humps of this curve. The question is, what's the largest that rectangle could possibly be? So what is the largest area the rectangle inscribed in f of x sine x can have?
No, we had a problem like this on a recent test.
Did we?
Not like that involved optimization.
Oh, yeah.
With the triangle.
It was
Yeah,
like
the
the
triangle.
the 1 over E.
Oh, yeah. Okay, that was, what was the deal with that one? I can't remember. That was a hard problem. I can't remember what it was.
I guess so.
You guessed on it?
No,
Yeah,
so I
no, I
guessed
did.
that, I
I
just
guessed.
happened to guess, but the side was like the right length, so then I kind of went with it from there.
Uh-huh.
That was
So I flat out
I
guessed
had
it.
to
right,
do
and
a
I
test
still
side,
got
it's not
it.
that question.
It was this one here, right?
Yeah.
Okay, so what was the deal there? That was a related rates question. It was saying like, if that point B is moving along the curve, then when is the area of the triangle not, what is the area when the area is not changing? Totally different than this, right? That's totally not optimization,
But
but
I do
There's a
remember having a
graph.
question like this last year.
Graph, so yeah.
yeah, we did a question last year that was like,
Optimization.
it was like a parabola, and you had to like maximize that
Yeah.
rectangular area, which is similar, but this one's a little harder, I think. The idea here was, let's just, to get a little jump start on it, the idea here, the easiest way to do this was to say, this graph is totally symmetrical, so if this is x, so is that. And then if the height is y, like if this parabola has the equation y equals like 4 minus x squared or something like that, you could say the area is equal to 2x, which is the width of the rectangle, times the height of the rectangle, which is y, and then just make that substitution. So this ends up being 2x times 4 minus x squared, right? And then you can differentiate whatever from there. So that's definitely a related question. Like, how could we adapt this process to this problem? I think it's a little bit harder, but it's the same idea. Any ideas?
Well, that is technically symmetrical, right? Like
Yeah.
a traditional sine curve is.
Okay, so one way to do this is to just split it down the middle, and let's say this is x and this is x. Okay, so now we have The area that we're trying to maximize is 2x times y again. But then how do you get y? Here, it was convenient because if this is x, if this distance right here is x, then that distance is f of x. But if this distance is x, that height is not f of x. Do you know what I mean?
Mhm.
Like if this distance is 1, this distance is not f of 1.
Isn't it just 1 minus, in parentheses, 1 minus sin x?
Wait, say it again?
1 minus, write this down.
Write this down.
1 minus, in parentheses, 1 minus sin x.
How do I figure that? This is
Or
this is
whatever
equal to
the-
sin x,
Okay, just the.
isn't it? I just distributed the negative.
I mean, I get what you're saying, because y can have those, y can't be more than 1, but.
Oh, so you're taking the maximum value. Hello?
Write this down.
Hey.
Hello. That was genius.
I'm just full of great ideas
Really
today.
insightful.
Can they wait till after class?
Oh, maybe.
Okay, thanks, I'll tell them. All right, bye. Chella and Paul, you guys have to move your cars, or they will be towed. But she said you can wait till after class.
I mean, I guess since I have been moving the codes, and the codes, I didn't move the code.
I moved some.
Yeah, I didn't.
It's expensive to get your car towed.
So,
So what do you think? All right, so all right, let me just get your thought process. So you're saying take the maximum value of this, which is 1,
1,
and subtract what now? You're
Oh,
subtracting,
He goes, no.
That's never mind.
you're trying to subtract that,
Yeah, but I don't know how to get that.
which you're saying is 1 minus sin x, but that's implying that this is sin x, which it's not. Right? So you're kind of saying that's why this ends up equaling sin x, because, but I get the mindset. It's a good thought process. It's a good thought process, but I don't think it works. Any other ideas?
does it help to know at all, like, the range of what x and y can be? Because, like, x has to be between 0 and.
That's a great point. X has to be between 0 and,
Pi.
no, pi over 2,
Pi over
right?
2.
Because this whole distance is pi, so that distance
Right.
has to be pi over 2, right? So that takes care of the endpoint aspect of it, but we still need to figure out the height of the function. If we knew, like, this x value, then we know that its height would just be f of that x value, you know what I mean? So if we knew what this was, like, let's give it another letter, like, say this point right here was the point A, right? Then the height would just be f of A. Bringing A into there, right? So how can we get A? That's the thing. I considered putting this question on the test, but I didn't think it was hard enough.
You did or didn't think? You didn't think it was hard enough?
Right.
Oh, okay. I love that. Well, I don't know how to do this one, so I probably won't know how to answer this.
Don't think that way. You get this. What do you think? Well, it's something minus x.
Isn't it, it's symmetrical, right? So when it's like, whatever the distance is from the origin to A is the same as the distance from x to pi over 2, like,
That's not true. This doesn't have to be right in the middle of that interval.
oh,
Like you could have a rectangle that's like this shape, or you could have a rectangle that's like this shape. We're just trying to find the biggest such
Right,
rectangle. It's
but-
not necessarily going to be the one that's in the halfway point.
okay.
You know what I'm saying? Okay. But isn't it true that this x value is really just pi over 2 minus x, whatever this length is? Doesn't that make sense? Because it's the midline minus x. And this one over here is gonna be the midline plus x. So isn't this really just gonna be the sine of pi over 2 minus x? Does that make sense? I think so too. So this would be, the area is 2x times the sine of pi over 2 minus x. And from here, it's easy. You just differentiate, so you equal 0. It's all like that. Does that make sense? But the setup of this one was pretty hard, I think. I was kidding about this question being too easy for the test.
It was a funny one.
I had it on there, and the test was actually just too long, so I took this. Okay, so, but what else do you think is a common mistake people would make in this problem if they got this far? Yeah, product rule. So you gotta just do the product rule, set it equal to 0, and solve. Let's go through it, actually. So this would be a prime, this would be the first times the derivative of the second. Chain rule, right? Plus the second times the derivative of the first. What do I do then? Yes! Absolutely, it's a calculator test. So definitely use your calculator. I was waiting for somebody to say that. Yeah. Don't be dumb. Use your calculator. All right, any questions on that? How is that challenging? Let's see. How about this one? Find two numbers whose sum
I need to do that.
Oh,
My question.
is 20 and whose product is as large as possible. So a non-geometric application. This is not a geometry problem. So you can't draw a picture. So what do? So I can't hear you.
Systems of equations.
Systems of equations. Okay, what do you mean?
So like x plus y equals 20, and then x times y equals another variable.
Product, okay. So what, then what?
Then solve for basic calculator.
Yeah, I mean, this is totally right. This is what we're trying to maximize. So you get it down to a single variable by solving for one of these variables. So you get x times 20 minus x equals p. So p equals 20x minus x squared. P prime is 20 minus 2x. Set it equal to 0, x equals 10. You do a little first derivative chart. You know x has to be somewhere between 0 and 20. If the numbers add up to 20, let's assume they're positive. I didn't write that, but assume they're positive. 10, you do a little first derivative chart, and you can see that it's positive and negative. There, so it's a max at 10. So the numbers are 10 and 10. So that one wasn't that hard.
Can you just do that up there?
Yeah, sure.
Yeah, that was like,
I'm just gonna scroll down a little. What if, how about this? Find the point on y equals radical x, which is closest to the point 4, 0. Can I scroll down now? Yeah. So the picture is, oops. The picture is, we have radical x, and we have the point 4, 0. And we're trying to find the point on the curve that's closest to it. So it's like there somewhere. Yeah, this is a distance formula problem, right? So we're trying to minimize that distance. So let's just let this be like x, y. So we're trying to minimize. Now think about this. If I'm trying to minimize d, which is really just the square root of x minus 4 squared plus y minus 0 squared, doesn't it make sense that that is going to be at a minimum when this is at a minimum? Right? If this is at a minimum, if the square root of a number is at a minimum, that's going to occur exactly when the radicand is at a minimum, right? Okay, so isn't this type of expression easier to differentiate than this type of expression? So that's what I'm going to do. I'm going to work with this because it's going to give me the same answer as if I minimize this. The point's going to be the same point. Do you agree? Everyone agree? Okay, so what do I do next? I can get rid of the parentheses over here. So this is x minus 4 squared plus y squared. Y is just radical x. So this is x minus 4 squared plus radical x squared. So this is, I'm going to actually just boil this out, x squared minus 8x plus 16 plus x squared minus 7x plus 16. Now I can just differentiate. D prime would be, and by the way, like, I kind of know that x has to be somewhere between 0 and 4, right? It doesn't make any sense that you're going to go this direction and get a closer point, right? So just the natural domain of this function is x is somewhere between 0 and 4. And actually, they actually equal that. So those are actual endpoints. So if I do this, this is giving me 2x minus 7, 0, x is 7 halves, rather. And that's it. And then you just have to do your first derivative test, like always, and make sure that it goes positive. Oops, in this case, it goes negative, positive. Right, we're trying to minimize the distance. So it has to be a minimum. And it definitely is. If you consider like this expression right here, it's a parabola shaped like this. It has to go down and then up. Its derivative is it's decreasing then increasing. Okay. Any questions on that? Any other questions on optimization? Doesn't optimization seem easier with calculus? Yes. Yeah, I think it's definitely easier with calculus than looking at the calculator. Okay, we're done. That's it. I'm going to stop recording now.
I don't want to.